Alright guys, this lesson is called Justifying Statements. What we're going to be doing in this lesson is stuff we've been doing all year long, which is great news. I'm going to give you a true statement, and you're simply going to back it up with geometrical truth. Sometimes your answer will be a property, sometimes it will be a definition, and sometimes it will be a theorem. So let's take a look at this. Alright, this is a baby step to get us to proof. Later, like on Thursday, I'm going to give you a triangle like this. I'm going to give you some given information, and you're going to go step by step, and you're going to prove those triangles congruent, doing an actual geometrical proof. Here is an example of what part of your proof would look like. Okay, so remember, I'm giving you a true statement. You're not deciding if this is true or false. You're explaining why this statement is true. If segment BD is perpendicular to segment AC, then ADB and BDC are right angles. So we know it's true. Now we have to pick something from here and decide why it's true. Sorry, what theorem or definition or property says if perpendicular, then 90 degrees? Good. Everyone go look at what number is that? Definition of perpendicular lines, number 15. You want to make sure your hypothesis and your conclusion match. Number 15, if two lines are perpendicular. If perpendicular. Check. Conclusion on here. Then they intersect at 90-degree angles, which is a right angle. Then right angle. Okay, the hypothesis and the conclusion match, so that is my supporting reason. That's my justification. And you're allowed to abbreviate definition of perpendicular line. Let's try another one. If BD bisects angle ABC, we lost some. When I opened this up, it lost some symbols in it. If BD bisects ABC, then angle ABD is congruent to angle CBD. I'm not asking you to decide if it's true. I'm asking you to tell me what theorem backs that up. Good. So it's like you're asking yourself, I know when I see this that I'm allowed to go to my picture and I'm allowed to do this. But what theorem is actually allowing me to do that? And you're right, it's a definition. And it's a definition of angle bisector. Very good. Next one. Segment BD is congruent to segment BD. I've been saying this all unit long. Good. It's the reflexive property of equality. And you are allowed to abbreviate property with prop. But I want you to write out the full word reflexive. Because some people get confused and they don't know if it's reflective or reflexive, and I want you to know the real property. So it's called the reflexive property of equality. A segment or an angle is congruent to itself. If D is the midpoint of AC, then AD is congruent to DC. Why are we allowed to say that? That is number one. I'll show reflexive is number one. Good. Definition of midpoint. What I want you to see here, what I want you to notice is that almost every time, in 1, 2, and 4, the answer is in the question. Look at that. Definition of perpendicular lines was the answer. What's in the hypothesis? Perpendicular. Number 2, definition of angle bisector. What's in the hypothesis? An angle and the word bisect. Number 4, the answer is definition of midpoint. What's in the hypothesis? Midpoint. So this is easier than you think. The answer is usually in the hypothesis. Let's try some more. If segment AE bisects segment BD, then BC is congruent to CD. Why are we allowed to say that? Definition. Good. This one is the definition of segment bisector. Because there's no angles getting bisected here. A segment is cutting in half another segment. Do you see the word midpoint? No. So if there's no midpoint in a hypothesis, Don't put midpoint as the reason. Oh, I lost all of these when I opened this file. Angle BCA is congruent to angle ECD. That's not even a hypothesis and a conclusion. That's just a statement. Good. Vertical angle theorem. Vertical angle theorem. If angle B and angle D are right angles, then angle B is congruent to angle D. I started this one because this is one I have never said out loud. So this will be new to you. It's not transit. Keep looking. Yeah, it's a weird one. Why does it even exist? It just does. It's called the right angle congruence theorem. That theorem says, what number is it for people watching the video? Right angle congruence theorem. 17. Number 17. There's a theorem out there that saves us a little bit of time. Let me write it down. Right angle congruence theorem. Instead of saying they're both right, and then saying they both equal 90, therefore they're congruent to each other, this theorem lets you skip that step. It says, hey, if they're both right angles, then they're both congruent. We get to skip one middle step. So that's why that theorem exists. All right angles in the universe are congruent, and that's the theorem that says it. Okay. Last one on this slide. If AB is parallel to ED, then angle A is congruent to angle E. Why in the world is that true? The other one. Yeah. Because they are alternate interior angles. And there's a theorem out there that says if lines are parallel, then alternate interior angles are congruent. And it's called the alternate interior angle theorem, and you're allowed to abbreviate it just like that. Okay, now I'm going to take something away from you. It's like when a kid is learning to walk. They like crawl, and now they're taking baby steps, but they're holding on to the coffee table. Okay, so now I give you the hypothesis. You don't just give me the why, you give me the conclusion and the why. And then by Thursday, I give you nada, and we do it all. Point D is the midpoint of AC. What can we conclude? Coffee table is gone. Yes, we did this in the warm-up. AD is congruent to BC, and now we do what we did on the other one. We just say why. And the answer is in the question. Okay, next one. Segment BD bisects angle ABC. If you don't know where to go here, if you feel lost, think, if they told me that, what would I add to my picture? If this angle just got bisected, I would do this. That's what I do when I see bisector. Then you just write down what those arcs mean. Those arcs mean angle ABD is congruent to angle CBD. That's what arcs mean on a picture. They mean congruent angle. And then, of course, okay, we're going to do these two more. Actually, I want to do these two. Okay. Given AB is congruent to BC, what can we conclude? Good. Angle A must be congruent to angle C. And why? Oops, not definition. I was too used to that. Called the isosceles triangle theorem. And I have mentioned that theorem a lot, okay? The converse of the theorem is when you're given angles instead of given sides. Does anyone know another conclusion we could have made? I give you a triangle and I say two sides are congruent. Could we conclude anything else? Do you see how this can go more than one way? Yeah. I tell you two sides are congruent. You could conclude it's isosceles. And your reason would be definition of isosceles. So this conclusion is going to be more helpful for proofs, but I wanted to let you know that this is not all black and white. There are different routes that we can take here. Last one from this part. AB is parallel to CD. What can we conclude? Very good. This is so important because I have students get this wrong all the time. Is it angle 1 is congruent to angle 2? Or is it angle 3 is congruent to angle 4? Because only one set of lines are parallel in the given. This is good. This is when you make your letter Z. Man, I trained y'all well. You make your letter Z. Oh, those are the angles that are caught inside the letter Z, 1 and 2, not 3 and 4. Thank you. Thank you. The reason why our good old alternate interior angles